At this point in the course, we should already have a sense that the slopes of inverse functions at points reflected over the line y equals x will have reciprocal slopes. So for example, if we were looking at the functions x squared, so let's go ahead and highlight these, x squared and root x. So we should hopefully know that these are inverse functions of one another. If we were to write f composed of g of x, they would give us x, and g composed of f of x would also give us x. That is to say, these operations undo one another. So if I were to look at their graphs here, we can hopefully kind of get a sense here that if I were to find let's go ahead and use a pen here, right? Something like this, if this were my slope here, this would clearly seem to be something like 1/2. And then if I were to kind of see that reciprocal slope or that slope at its reciprocal point, we see that the slope here would be about 2, right? So we can do that pretty much at any step, any x value and see its inverse point and see that those slopes should be roughly reciprocals of one another. So that's something that we kind of hopefully came into this course with an intuition for. What we want to do now is we want to actually look at the inverse functions derivatives and actually look at their actual derivatives and not just the numeric slope values at specific points. So let's take a look again at those same functions and let's find their derivatives and see if we can come up with any observations about the two. So starting with f of x, let's write the inverse of f of x. So f prime of x, well, that's a pretty easy derivative. That's just going to give us 2x. Okay. Now, what about g prime of x? Well, if we can write g of x as root x, or x to the 1/2, then this would be equivalent to 1 over 2 root x. Now, when we're looking at these two derivatives, they're close, but they're not quite reciprocals of one another. They're not exactly reciprocals, I should say. They look like there is some type of reciprocal relationship, but not quite the same, right? G prime of x isn't just 1 over 2x. But could we rewrite g prime of x in terms of the reciprocal of f prime of x? That is to say, g prime of x, we see here that this is, up to this point, looks like it's the reciprocal of f prime of x. But if I replace that x now with, but what we have here is that root x. But if I replace that, what we've done is we've replaced, let me actually just do this in a different color. We've replaced that x with a root x here. Well, where else do we see that root x? That root x is exactly g of x here. This is g of x. So maybe another way of thinking about it is as such. Let me go ahead and write f prime of x is equal to 1 is 2x. What is the, if we said that f prime of x is equal to 2x, the reciprocal of this would be 1 over 2x. Now compare that 1 over 2x with 1 over 2 root x. Compare these two. Let me actually just put them side by side. Is there a way in words that we can write out exactly what's happening here, what the relationship is between the derivative of f of x and the derivative of g of x? I'll give you a moment to kind of pause and think about that for a bit. And hopefully what we can say in words is the following. We can say that the derivative of our function, or f prime of x, is the, it's the reciprocal of the derivative of g of x, which was our inverse. I'll write that in parentheses here or brackets. The inverse composed of f of x. So the derivative of our function, okay, the derivative of our function is the reciprocal of the derivative of our inverse composed of our function. And I'll say that one more time just to make sure that this gets hammered home. If we know that two functions are inverses of one another, we can say that the derivative of our function is the reciprocal of the derivative of our inverse composed of that same function, and vice versa as well. Well, why is this the case? I mean, this just seems initially like it's just a nice kind of coincidence here just based on these two functions, but will it work for every function? And yes, we can actually analytically and algebraically show that it will be true for every type of function using the chain rule. So remember, if f and g are inverses, if f and g are indeed inverses of each other, that means f composed of g of x will be equal to x, and g composed of f of x will also be equal to x. That's something that we learned in pre-calculus about inverse functions. If I were then to differentiate this exact equation or this statement here, we can then say the following. What is the derivative of this? Keeping in mind the chain rule, we can say f prime composed of g of x times the derivative of our inner function times g prime of x. All of that is equal to the derivative of x, which is just 1. Now, if I wanted to isolate just g prime of x, for example, I could say g prime of x is equal to 1 over f prime composed of g of x. Now, if you look at that statement here and what we've just written out above, think about what we've just said. We're saying that the derivative of a function is the reciprocal of the derivative of our inverse function composed of our function itself. And if we keep that in mind, then we can make that generalization as what we've just written here. And that gives us a good understanding of how inverse function derivatives are going to work moving forward. And so we can start looking at things like inverse trigonometric functions. But let's just do a little bit of practice just to make sure that we understand the structure of these derivatives of our inverses. So let's look at this first practice problem here. So given the table of values for f and the fact that g is the inverse of f, so f and g are inverses, determine the following if possible. And if it's not possible, let's make sure we understand why. So let's kind of zoom in on this table first. So I've given you a table here, and something that I like to do, something that I found to be pretty helpful, is to come up and rewrite this table as a set of ordered pairs. Okay, so for f here, we're going to write the ordered pair -1, and the y value would be 1. At 0, I would get 2, and at 1, I would get 5. And the slopes at each of these points are given to us. F prime of x evaluated at these points, so f prime at -1 is 1.5 or 3/2. And so we can write these slopes as well. Now, the big reason why I like to set it up this way is just one, I'm just visually a learner, just visual learner, so this just helps me see the structure a little bit better. G is equal to the inverse of f, which means I can rewrite these coordinates. The inverse just simply means I switch the domain and range. So this would be 1, -1, 2, 0, and 5, 1. And I know that the slopes, the numeric slopes, should be inverses of each other. Not to say anything about algebraically what's happening with the inverse functions, but the slopes should be inverses of one another. So I can then say the following. So using these now, let me go ahead and just make this a little smaller. Using these now, can we evaluate a couple of these inverse or these derivatives? What is g prime of 1? So g is the inverse of f. So what is the derivative of g evaluated at 1? Well, we just found that. We can easily, that would just be 2/3. Now, suppose I wanted to do this algebraically. We don't have to, but if I wanted to do this algebraically, let me just kind of pause and also show that. If I wanted to find part A algebraically, I could say that the derivative of g evaluated at 1 is the reciprocal of the derivative of our inverse, in this case it's f, evaluated at our function, g evaluated at 1. Well, going back to our ordered pairs, what's g of 1? Well, that would be 1 over, or the reciprocal of f prime evaluated at g of 1, which is -1. What is the derivative of f evaluated at -1? That's 3/2. So that would be 1 over 3/2, which is how we get 2/3. All right? Well, go ahead and pause the video and see if you can work on the rest of these. Well, hopefully you found that g prime of 2. So the derivative of g evaluated at 2 would be 1/2. The derivative of g evaluated at 3, well, we don't actually know the slope at 3. We're only given the x values for g at 1, 2, and 5. So this is unknown. And we can say the same about part D as well. These are both unknown. We don't actually know the slopes at g of 3 and g of 0? Well, we do, however, know the slope at at x is equal to 5 for the function g. So we would say g prime of 5 is equal to 2. G prime of 5 is equal to 2. We got that there. Okay? All right, let's try another problem now. Let's try this next one here. So let's say that g is a differentiable function. Let me just kind of zoom in on this. G is a differentiable function with selected values given. We're going to use the table or use this information to answer these questions below. So starting with part A, let's estimate the inverse using the table. So just like I did before, if we have g here, I'm going to set it up as ordered pairs. So 2, -2 with a slope of 4. 4, 5 with a slope of 1. 6, 2 with a slope of -3. Okay? All right, so for part A, let me just do this here. Part A, let's find the derivative of the inverse of g evaluated at 5. Okay? So we can set it up as follows. We can say, all right, let's look at this for a second. Let's think about this for a moment. The derivative of the inverse of g is equal to 1 over g prime evaluated at the inverse of x. Okay? So we can then say g prime. What is g inverse at this case 5? G inverse of 5? Well, that would be 4. So let me actually just replace this x with 5. Okay, so the inverse evaluated at 5, well, that would just be equal to 4, right? We're getting that from this ordered pair here. So what is g prime of 4 here? I actually probably should also replace this with 5, just to make sure we understand what we're saying here. What is the derivative at 4? Well, we know at 4 the slope is equal to 1. Slope is equal to 1. So this is 1 over 1, which is just 1. So that's part A. Let me actually move this here so we have some space to work with. For part B, let me switch to a different color. All right, so now part B. So this one here, we have the function p, and p is defined as being the inverse of f times g of x. So we are asked to find p prime of 2. So let's start by finding the derivative of p. What is just p prime in general? So using the product rule, we can say that it is f inverse prime of x times g of x plus f inverse of x times g prime of x. Okay, and just applying the product rule. So now I am going to evaluate my inverse at 2. So what is f inverse prime evaluated at 2? Well, let me switch colors here because there's a little bit of work that we have to do with this. Okay, let me actually just kind of move over here. Let's think about this for a second. What is f inverse of 2 in general? Just think about this. What is f inverse of 2? What we're effectively asking ourselves is, when is this equal to 2? That's what we're asking. And this is a little challenging to do algebraically. So I'm just asking that you just kind of look at this, look at the structure of this equation and just try to figure out for what values of x would all of this be equal to 2. And hopefully you see that when x is equal to 1. Therefore, we can say that the f inverse evaluated at 2 is equal to 1. Okay? So, and that makes sense. If you have 1 plugged in here, you would have 1/2 over plus 3/2. That gives us 2. Natural log of 1 is equal to 0. So that's just what gives us 1. Okay. So now that we know what our inverse is evaluated at 2, we can then continue on and ask, what is the derivative of our inverse evaluated at 2? Well, we know that is 1 over f prime composed of f inverse of 2. Okay? And we just said this is f prime. F inverse of 2 we just found here as being 1 in the previous step. So what is f prime of 1? So we would say f prime of 1, we would need to actually find now the derivative of f. So let me do that in a separate color because I just don't want us to get too confused here. F prime of x, if we evaluate this is going to be the derivative of x squared over 2 is just x. The derivative of 4 times the natural log of x is 4 over x. So now let's evaluate this derivative at 1. That's 1 plus 4, that's equal to 5. So we can then say this is going to be equal to 1 over 5. So now that we've done all that heavy lifting, we can now say that f inverse, that derivative evaluated at 2, is equal to 1 over 5. Okay? Now, what about g of 2? Let's go back to our table. What is g of 2? Well, that's going to be equal to, let me just switch to a different color now. G of 2 is equal to negative 2. Got that from our table. What is f inverse evaluated at 2? The inverse of f evaluated at 2, we did that here. That was equal to 1, right? So let me actually highlight that. So we can say plus 1. And then was g prime of 2? Effectively, what is the slope at g is equal to 2? We said that is equal to 4. So again, we got that from our table. And then from here, we can just clean this up. We can say this is negative 2/5 plus 4. If we want to combine these, that would give us 18 over 5. Okay? All right. I'm going to have you pause now and pause the video and go ahead and see if you can work out part C. It's a similar kind of structure here, but now we're doing this where Q is the quotient of the inverse of F divided by the inverse of G. Okay? All right. So for part C, I'm going to try to see if I can make some space here. Part C, we're going to say Q of X, again, just to write this down, it's the inverse of F divided by the inverse of G. Okay. So what is Q prime of 2? Well, Q prime of X, using the quotient rule, is going to be all of this. Careful of my notation here. Okay, so that looks pretty gnarly, but that's just the quotient rule, effectively. Okay, so let me make some space now. All right, now what is Q prime of 2? Okay, so we're going to, fortunately now that we've done that setup, we did most of the heavy lifting in this previous problem. So we can just really plug and chug from what we have written down from these. So I'll actually zoom out for this. What is F inverse prime evaluated at 2? So we're going to do this. I wrote G prime of 2. I apologize. This should say Q prime of 2. So that was this right here, 1/5. G inverse of 2, that just gives us positive 6. Okay, we looked at this part of the table here, or I should maybe say this part right over there. F inverse of 2, we found that here as well. That was positive 1. We got that up here. G inverse prime of 2, and that one we actually do have to evaluate. We got to actually figure that one out. So let's do this. Just circle this so you know what I'm finding here. That's going to be G inverse prime of X, first off, is 1 over G prime of G inverse evaluated at 2. And we know that that is 1 over G prime at G inverse of 2 is going to be 6. We got that from our table, again, from right over here. G prime, oops, sorry, my notability just seemed to crash. Sorry about that. All right, sorry about that. All right, technical glitch. And that's going to be equal to 1 over, in this case, G prime of 6. And just to finish this off, that should be 1 over negative 3. Okay, so now we can plug in negative 1/3 over here. And I should probably change my colors just so keep it consistent. Make that purple as well. All right, so now that we have all that, we can finish this off. And this is all over G inverse evaluated at 2, which is going to be 6. So that's 6 squared. So this is going to give us this plus 1/3. All of this over 36. And I'm okay with you leaving it like that. But if we needed to clean this up, we can just write this as 18 over 15 plus 5 over 15 over 36. And that should give us 23 over 15 times 36. And I don't have a calculator on me, and I'm a little too lazy to figure out the rest. All right? So I know that it can look a little daunting, but if you take your time and really remember the structure and just go back and forth between understanding what the derivatives of our inverses are, then I think these are definitely approachable.